So we are going to talk about integral calculus now, right? So 5.1, introduction to integration. Okay. And so roughly speaking, the goal is to find the area under curves. To find the area of curvy things. So you have some function, right? And you're wondering what the area is under the curve. And what we mean by area is actually what's called assigned area. Okay, so by assigned area, we mean that we're going to take this area above the axis to be positive, and we're going to take the area below the axis to be negative. Okay, so so you could have something, if something balances out, you could have something with a sort of a zero area. Okay, so assigned area where the things above are positive and the things below are negative. Okay, so as usual, there's only one idea. Okay, there's only one idea in calculus, and that is the unknown can be analyzed as the limit of the known. So I mentioned this. We said that you take a simple idea and you combine it with the notion of limit, and that's basically calculus. Okay, so here's what happens. Somebody says like, here, find the area under this. Okay, find the area under this curve, right? And so what you do is you say, okay, I don't know how to find this area, but I do know how to find the area of a block. Okay, I do know how to find the area of a box. Right? That's something that any child is taught. What's the area of a box? What's just the base times the height? Right? Okay. So you say, okay, I'm gonna make a box, and that's gonna be my guess. That's gonna be my guess for the area. Okay. And you say, okay, and then what I'm gonna do is I'm gonna chop the base in half. And I'm gonna make two boxes, each of which is some approximation. So I'm gonna take maybe this box and this box. Okay. So you take another. In your second step, you break the base into two pieces, and then in the third step, you break the base into three pieces, and you take some. You could take it like this, and like this. Right. Oops, that's a box. Okay. So you keep on taking. You keep on breaking the interval into smaller and smaller pieces, right? And on each piece, you take some approximation of your actual area. Right? So you take these boxes, right? And these are all things that any child could deal with, right? You say, if you ask the child what's the total area of these boxes, well, that's just multiplication and then addition, right? So you say, okay, I can make some guess. I'm going to take the areas of these things and then I'm going to add them all together, right? And so what you do, however, what you do in calculus is then you take the limit as the number of partitions of the base tends towards infinity. Okay, so you let the partitions become basically finer and finer, and let the partitions become infinitely fine. We'll let the fineness of the partition tend towards infinity. Okay, and that's basically what you do to find the areas. Okay, so so that's the idea of integration, and we'll get to it more properly in a second. But does that make sense to people? Right? To find the area of something complicated, take the area of something take areas of something that you do know, and then take the limit as you become infinitely fine. Okay. Any questions? Okay. So Okay, so we're going to need something called summation notation to make this easier to talk about. Okay, summation notation. If I write let a sub I be a sequence. Okay, so you have a sequence of numbers. If I write something like this, I equals m to n, where m and n are integers, are whole numbers. Okay. And I write summation a sub I. So this is read the sum of a sub I from I equals 1, I equals m to n. Okay. What that means is I'm going to take my sequence and then sum those elements. I'm going to sum a sub m plus 1, a plus m plus 2, all the way up to a sub n. Right, so if I write something like this, if I write summation a sub I equals 1 to 5, that means I'm going to take the first 5 elements, right, and sum them together. A1 plus A2 plus A3 plus A4 plus A5. Right, if I write summation I equals 10 to 100, I'm going to sum the guys from 10 to I10, A sub 10 to A sub 100. If I write from I equals 1 to 1, then it just means that one element, right? Just that one element. Yeah, go ahead.
What are the numbers on the last one?
I equals, summation of the a sub I from I equals 1 to 5 is A1 plus A2 plus A3 plus A4 plus A5.
I see. Okay.
So those dots just indicate the guys who are left out. Okay, write them all in since it's not that many. So this term is called sum or summation. It's the Greek capital S, sigma. S for sum. So just a couple of examples to make sure that you understand what we're doing here. If I write a sub I equals I, so I have a sequence here. A sub I equals I. Okay, here's my sequence. The ith element is just I. So A1 is 1. A1 is 1, A2 is 2, A3 is 3, etc., etc. If I write summation I equals 1 to 100 of A sub I, well, what is that? Take 5 seconds and write down what that means to you. Okay, what is it? Anything? Good, you want to say?
No, I've written the a sub 1 plus dot 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 a sub 100.
Yeah, that's true. So a sub 1, that's a legitimate answer, right? A sub 1 plus a sub 2 plus a 100. And remember what these things are. A sub 1 is 1, right? A sub I is I. So this is actually 1, this is 2, this is 100. Right? Is everyone okay with that? Okay. Usually, so there's a quicker way of writing this. People usually just write it like this. Summation of I from I equals 1 to 100. Right? Rather than write a sub I is I, summation of the a sub I, you could just write summation of I from I equals 1 to 100. Right? That's the same. Just be more succinct. If I write summation I squared, I equals 1 to 100, what's that? Somebody just tell me. What is that? Alpha. Exactly. Yeah. 1 squared plus 2 squared plus 3 squared plus all up to 100 squared. Right. If I write, say, summation n equals 1 to 100 over 1 over n squared, what's that?
1 over 1 squared.
Exactly. Right. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 100 squared. Okay. Is everyone okay with the notation? Anyone have questions about it? Okay. Just for fun, does anyone know the sum of numbers from 1 to 100? Has anyone been punished in their childhood by having to sum numbers from 1 to 100? No, you haven't? What kind of a world is this? Okay, so does anyone know the formula for sums from 1 to an arbitrary number? If you take 1 plus 2 plus 3, blah, 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 up to n, does anyone know the formula?
It involves parentheses.
It involves parentheses. That's very good. It does.
It involves an n and I think a 1 somewhere.
Okay,
You're
yeah.
adding
Yeah, very good, very good. So the sum from 1 to n actually turns out to be n plus 1 over 2. N plus 1 over 2. Yeah. There's a formula for the squares. I always forget it though. I don't remember the formula for the sum of squares.
Isn't it, n plus 1, and then 2 n plus 1?
Over 6 or something like that. Right. I think that's right. Yeah. So I squared equals 1 to n. This maybe. That's right. Okay. Yeah. Yeah. This is actually a pretty famous formula, and this is a famous problem. There's a story behind this problem of the mathematician Gauss. Who many people regard as the greatest mathematician of all history, Gauss. So the story goes that when Gauss was 8 years old, his class was bad. His class was being too loud, and the teacher said, "Okay, everybody, shut up and start adding numbers from 1 to 100." So all the kids are like, "Oh," and they start adding numbers 1 plus 2 plus 3 plus 1. But Gauss just sort of sits there and stares off for a minute. And then he writes something on his board, and he hands it in. Right? And he's in the end, he writes 50-50. Right? And in the end, he's the only one who got the right answer. Apparently by figuring out the formula in the meantime and then using it.
Great.
So he was 8 years old, whatever. Yes.
I think I heard the same story, but I think someone said that someone did it where like they did 99 and 1.
Yeah.
And then they found all
Yeah,
the
maybe
numbers.
that's the easiest. Maybe he did it that way.
Okay.
That's quite possible. Right? So that he said, well, look, if you're adding 1 plus 2 plus up to 100, right? Then you just look at the sum of the first and the last. It's 101, right? And then second to 2 plus 99 is 101, right? And that happens, I guess, 50 times. So you get 50-50. But even so, however you did it, it's pretty amazing. Yeah. Okay. Okay. There's actually a story behind this last one as well, with the sum over n squared. Does anyone know what happens to the sum over 1 over n squared as n goes to as you keep on going? It actually tends towards a number. I squared over 6. So the farther you go out, the closer you're going to get to pi squared over 6. But to show that actually is not easy at all.
Wait, yeah, what is the numerator if you're just adding like
Yeah. It should be sort of shocking to you, actually. Okay. Ria, you were right. I actually have it written on This is right. Okay. 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 So we're going to do something now called the right endpoint approximation. Endpoint approximation. Okay, so this is your approximating area. Okay. And here's one way to approximate areas called the right endpoint approximation. Okay. So it's going to be a little bit theoretical looking, but it's going to look a little abstract, but it's actually something very concrete. So it's like this. You have some interval. Okay. And I should say maybe the nth right endpoint approximation. So you have some interval, and you have some function over that interval. And what you do is, one, you divide the interval AB into n subintervals, each of equal length. Okay. What's the length of each interval? What's the length of each interval? Yes, one more time. B minus A over n, right? Because the total length is B minus A, and you divide it into n parts, right? So each of equal length, which will abbreviate as delta x, but it's really B minus A over n. So we're going to call that length delta x, the change in x. Okay. So we divide. We divide this thing into n intervals of equal length, and we call the endpoints x0, x1, x2, all the way up to xn. Call the left endpoints of the intervals, of the subintervals, x0, x1, all the way to xn. And x0 is A, and xn is B. Okay. We call this collection x0, x1 to xn the uniform partition of order n. Uniform partition of AB of order n. Okay. So just to give you some language, right? We call these. You take an interval and then you split it up into equal parts. We call that sort of splitting a partition. That's a term we'll use pretty often. Okay, so we have a partition of AB here. Okay. Okay. So then what we do is we define this thing called. Everyone all right? Should I hold on? Okay. So then what we do. Okay. So what's going to be our right endpoint approximation? For each interval, we're going to take the right endpoint. Okay, we'll take the right endpoint, and we'll take the height the height of the function at that point, and we'll multiply by the width of the base. Okay? And so we'll get the area of a rectangle. Okay. And we're going to do that on the next interval as well. We'll take the second interval, take its right endpoint, take the height of the function at that right endpoint, multiply by the width of the base, and we get the area of a second rectangle. And we're going to take all of those things and add them together, and that will be our nth right endpoint approximation of the area. Okay, so the idea is pretty simple, right? We call, let me write it here. We take summation f of xi, right, as I ranges from 1 to n, and multiply those heights by the width of the base. Remember, the width of the base is b minus a over n. This thing, this value is called the nth right endpoint approximation of the area under f on A. So this whole thing, you can think of this whole thing as one really long definition. Okay. It's the definition of this term, right endpoint approximation. Okay. So just to do a simple example. Here we have f of x equals x. F of x equals x. And we're going to take it on 0, 5. And I'd like to know what is the fifth right endpoint approximation. What's the fifth right endpoint approximation? Okay. So take 1 minute and see if you can write down an expression for that. See if you've understood the definition. Okay, turn to somebody next to you and say what you're doing. Mariah, you're by yourself. Just talk to yourself, Mariah. Okay. Would somebody like to talk about it? Would somebody like to say anything? So what do we need to do? We need to take the base and divide it into five intervals, right? So what do? What's going to be the length of each interval? 1, right? So 2, 3, 4, right? 1, 2, 3, 4, 5. That's our partition, right? So our partition, the partition is 0, 1, 2, 3, 4, 5. Right? And then what are you going to do? You're going to take the function and evaluate it at the right endpoint. Right? So you take f at 1 and multiply it by the width. Right? Well, that's just 1. Right? You take f at 2 and multiply it by the width. That's 1. F at 3, multiply it by the width, which is 1, multiply it by 4, and 1 plus f at 5. Right? And whatever that number is, maybe we can work it out, of course. You can write it out in a fancy way. So that's going to be, of course, that's going to be 1 plus 2 plus 3 plus 4 plus 5. 15. Yeah.
Oh, maybe it doesn't matter. I wrote like I equals 0 on the bottom, but does that not matter? Because it's just 0.
You don't want to use I equals 0 because that would give you f of 0 times 1. That's sort of throwing in an extra term, right? Because the right endpoint approximation says you want to take, you start with the first interval, take the right endpoint, multiply by the length. Okay. Take the second interval, take the right endpoint, multiply by the width of the base.
Isn't like x of 0 though equals a, and 0 is the endpoint?
Yeah, but we want the right endpoint. For
Right.
each interval, we want the right endpoint.
Okay.
Let me change the problem a little bit. So if I had something like this, 1 through 6, say. Okay, 1 through 6. Well, then what should I write down as the approximation? Well, again, right, you're going to take, right, so now you're, right, now your partition is going to be 1, 2, 3, 4, 5, 6. Right? And what's going to be the fifth approximation? What will it be now?
Still 15.
Hmm?
Still 15.
Still 15? Are you telling me that the area under that is the same thing as the area under this? If we keep on stepping over, the area is not going to change? Tell me, what is just tell me what the right approximation, somebody tell me what the approximation is. Well, you're going to, maybe that's what's confusing. What do? You take f at 2, right?
You're leaving out f of 1?
Mm-hmm. Right, because here we're doing it on 1 through 6. Okay. Here we're using the same function, but now we're doing it on the interval 1 through 6. Okay. Maybe it's clearer now. Okay. So what's going to be the right endpoint approximation here?
Right.
20? Right. How do you get it? Well, you say, you're going to take f at the right endpoint, right, and multiply by the width of the base. So f at 2 times 1 plus f at 3 times 1 plus f at 6 times 1, which turns out to be just 2 plus 3 plus 4 plus 5 plus 6. Is that clear? Okay. What if I said, let's see. Just to make it a little bit tricky, what if I said I want 2 through 6, I want the nth right endpoint approximation. I want the nth right endpoint approximation. See if you can write down an expression for that. I want the nth, right, endpoint approximation. So just, you're just going to use the number n rather than the number 5. Okay, turn to somebody nearby and say what you're getting. Say what kind of expression you have.
Oh, we were gonna use it too. But then it's just like 6 minus 2 minus 10.
Yeah. That's change delta x.
6
And it's like at the bottom.
Okay, does anyone have an idea? Let's make some guesses as usual. Let's make some guesses. What do we need to do? Somebody tell me what we need to do. Well, okay. B minus a over n, so we need the width of the base, right? We're going to divide this thing into n pieces, right? I don't know what n is, but n is some number, right? You divide, so what's the width? 6 minus 2 over n, that's right. So you got 4 over n is delta x, right? Okay, and then what we want is to evaluate f at x of I from I equals 1 to n times delta x. Right? We want this.
I equals 1 again, or I equals 2?
Well, remember, we're going to call each of these, this is x0, x1, x2, x3, up to xn, right? So we partition the interval into n pieces, and we're going to call the dots involved, the points involved, x0, x1, x2, x3, right? And we're going to evaluate f. We're going to evaluate f at x1 and multiply by the width of the base with the value at x2 multiplied by the width of the base, et cetera, et cetera.
So I is dependent on the start point.
Well, so here's the question: how do we express these guys? What is xi? What is xi? Right? It was so simple over here, but now we're being a bit more abstract, right? It was easy to do here. What is it here? What is x0? X0 is 2. That's easy, right? X0 is 2. What is x1?
Well, no, whatever the next plus n. Yeah. 2 plus n.
2 plus n? So like n, if n is 100, then it's going to be 202?
Oh, it's
Kimai. 2 plus what? 2 plus 4 over n, right? 2 plus 4 over n, right? Because the width of each interval is 4 over n. 2 plus 4 over n, right? What's x2? 2 plus, I'm going to say 2 4s over n, right? What's going to be the jth dot? What's going to be what's x of I?
2 plus I times 4 over n?
2 plus I times 4 over n, etc. Yeah.
So x sub 1 or x sub 2 isn't the area of the triangle for the rectangle, or it is?
X sub 1 is just the point. So here we're calling this point here x0. We're calling this point here x1.
Okay.
This point is x2.
So it's not the rectangle itself?
It's not the rectangle itself, it's just the right endpoint. It's just, these are just the endpoints of your intervals.
Okay, cool.
Right? But you evaluate, you take your function, right? So here's xi minus 1, xi. You take your function and you evaluate it at xi, and you get a height, right? So this is the height on the I interval, right? And then this is the width of the base. This is the width of the base. You take the height times the width of the base, and you get the area. Right? Altogether, this thing is the area of the I rectangle. Okay. And then you add up all the rectangles. You add up all the rectangles, and you get the end, right endpoint approximation. So just to spell this out more clearly, so this thing then is going to be summation f of 2 plus I times 4, I'll get like this 6 minus 2 over n, times 6 minus 2 over n, like the delta x. This is the delta x again. From I equals 1 to n. Okay, you see, yeah, Claire?
So the 2 plus I, 6 minus 2 over n, that's just x1.
Yeah, that's your xi.
Oh,
This
or
whole thing
xi,
together
yeah, okay.
is your xi. Okay, but notice that really, we're not really doing all that much different from over here. You're just doing the same thing that you would have had to do, right? Here's your left endpoint, you add on the width of the interval, right? And you multiply by the width of the interval. Right? You add on this to get the appropriate endpoint. You evaluate the function there and multiply by the width, and then you add them together. So it's the same thing, it's just more abstract because you've got i's and n's rather than, i's and 5. Right? Earlier we did n's 5. Everyone okay? Anyone confused? Okay. So if I change this to say a, b, right? What would I need to do to change my expression over there?
He said 6 and 2.
Yeah, just replace the 6 and 2 by b and a. Right. Is that clear? Okay. So, okay. Any questions? Madeline, you have a question? You do have a question. Great. Yeah.
So will it always be that the sum is f of x of 0 plus I of b minus a over n times b minus a over n?
Yes.
Okay.
Yes. Yes. So this is actually maybe a more explicit way of writing out the right approximation of f on b over a, on a comma b. Excuse me.
Mm-hmm.
Yeah.
Okay.
Maybe we should use this as the definition, but it sort of misses the. I mean, it's the same thing as the definition, just more notational rather than conceptual.
Yeah. Okay.
Yeah, it's exactly the same thing. Okay, so I'm going to do an example. No. So here's the definition now of what we call area. Okay, so given some function over some interval. Okay, so here's some function f, and you're looking for the area A. So given this sort of thing, the area A is defined as A is the limit, as n goes to infinity, of the nth right endpoint approximation. Okay, so I'm going to write it out. nth right endpoint approximation. Right. Maybe it's better to write it like this: the limit as n goes to infinity of summation I equals 1 to n f of a plus I times b minus a over n times b minus a over n.
That works for every function.
Yeah. Yeah. So this is a way of finding an area. Well, it doesn't work. It works for continuous functions. If your function is too crazy, then it won't. It won't necessarily. So what you do? Yeah.
Is the whole thing multiplied by b minus a? And what's multiplied by that?
It's the summation of the height times the width of each rectangle, and you sum over all rectangles. Okay, I'm gonna sort of rush through an example here. Here's the example. So 0 to 6, and you're taking the function f of x is 2x. So, okay. So if we want to find the area under this using the right endpoint approximation, what you do is you say, okay, well, I'm going to take the nth right endpoint approximation. Well, that's going to be summation f of 0 plus I times 6 over n times 6 over n from I equals 1 to n. Right? You divide this thing up into n pieces. Right? Each of them has the width of 6 over n. You say, okay, I'm going to take 0 plus I times 6 over n, evaluate f there, and then I'm going to take multiply that by 6 over n.
The interval is 0 to 6?
Mm-hmm. The interval is 0 to 6. Okay. Okay. Well, my function is 2x, right? F of x is 2x. So what's f of this? F of I times 6 over n is going to be what? The height, yeah. So what is it? If my function is the thing that takes in x and spits out 2x, it takes in this, it's going to give me
2 times.
twice that, right? So I'm going to get 2 times I 6 over n times 6 over n. Right? What does that give me? That gives me 72, right? 6 times 6 is 36, times 2 is 72. Right? 72 over n squared times I, summation I equals 1 to n. Yeah, quick.
What about the 6 and then it's multiplied by? Or are we just doing the height right now?
No, we put it all together, right? Here's the 6, right? This is the f of this
Oh, I
turned
see.
into this.
I see.
The 6n is this 6n.
Gotcha.
Multiplied together.
Got it.
Right? Okay. Okay. Now, this 72 over n squared is, each of the i's is multiplied by it, right? So I have 72 over n squared times 1 plus 72 over n squared times 2 plus 72 over n squared times n. Right? So I can pull the 72 over n squared out. Right? I get 72 over n squared times the sum of I from I equals 1 to n. Right. Okay. 72 over n squared times summation I equals 1 to n. Because each of those things is multiplied by the same number, 72 over n squared. I can pull that up. Okay. And now we use the formula that we mentioned before, right? The one that involves parentheses and the one. Right. And so we get this. This is the nth right endpoint approximation. This is it, right? 36 and n plus 1 with n squared.
So that's the area under,
That's the nth right endpoint approximation. And to find the area, we need to let the intervals become infinitely fine. So take let n go to infinity, and what do you get? What do you get? N times n squared, n times n plus 1 over n squared. What does that tend to as n goes to infinity? 1. Right, so you end with 36. So the area of this triangle is 36, which you knew already from elementary school. But Claire first.
I don't understand how you got from the 72 the one on top to that one.
From here to here?
Yes.
Summation of I from I equals 1 to n, we have that formula. You add 1 plus 2, blah, 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 up to n. So
Okay.
use that formula.
Okay.
Yes, Stefan?
Why did you start multiplying down there? Down left. Down left. Yeah, why did you start multiplying by 1 and 2 and 3 and all the way to n?
I was just writing this thing out. What is this? This is 72 over n squared times 1 plus 72 over n squared times 2. Just to show you that I can actually pull. I don't need to write this part. You can erase it. Right?
It was just for the.
Just to show you that why I can pull the 72 over n squared out. Yeah. Okay. So you end up with this amazing fact that the area of this triangle is 36, which you could have done by easier methods. But this is what you use for more complicated things. Okay. So we'll do more of this next time.